is miserable. And this is good because it is predicted to have a fairly low pH. Okay, any questions? Right, then we go on to 7.3.2, where they said calculate the mass of zinc hydroxide initially present in the flask if the initial concentration of the HBr was 0.45 moles per decimeter cubed. Okay, so again, this has got to go down to working with the number of moles. If I look at my equation, my zinc hydroxide, I'm not going to write out the full thing. My zinc hydroxide reacts with 2 moles of HBr. Okay, your mole ratio is really important, so you need to make sure that you write it down. Check that your equation is balanced, and then figure out what you're working with, and make sure that you have a look at the mole ratio. So the mole ratio over here is 1 mole of that reacts with 2 moles of that. Okay. The only thing is that I don't know how many moles. How do you get the concentration on? Sorry, the question was, how did I get the concentration of the HBr? That was over here. Sorry, this is really rather messy. It's the number of moles that remained in the solution after I've added the zinc hydroxide. So that I calculated using the back titration. I got 8,25 times 10 to the negative 3. That was the number of moles, and I divided by the volume. And the volume, they told me, didn't change, so it stayed 90 cubic centimeters. But remember, you have to change the 90 cubic centimeters to decimeters. So that's where I got the 0,09 from. And when I divide the one by the other, I get 0,092. Okay, that was the concentration of my HBr. And then you've got to remember that when you break up your HBr, when it donates a proton, it's 1 proton for every 1 HBr. So if I have a concentration of 0,092 moles per decimeter cube of HBr, and it dissociates completely or ionizes completely, I would have 0,092 moles per decimeter cubed of H3O plus. Okay, so I just need to double check that the ratio is 1 to 1, and then I can use the same concentration over there. I hope that clears it up. Okay. Right, so I know that the mole ratio of my zinc hydroxide and my hydrogen bromide is 1:2. But I don't know how many moles of hydrogen bromide I had right to start with. Okay. So in the beginning, I had 90 cubic centimeters of my HBr. I added my solid zinc hydroxide to that. Okay. I ended up with a mixture that had an excess of HBr in it. I titrated that against sodium hydroxide. And I figured out how many moles of HBr I had in excess when this reaction had finished. Okay. If I can figure out how many moles is in my HBr to start with, I knew how many moles I was left with at the end. Okay. So if I take the total number of moles, and I know that that is equal to the reacted moles, oops, spelling, plus my excess. Okay, so if I go back to what I was given, I have now been told that the initial concentration of the HBr is 0,45 moles per decimeter cubed. Okay, so I know that I'm starting with a concentration of 0,45 moles per decimeter cubed. And I know that my volume is 90 cubic centimeters. If I have the concentration and I have the volume, I should be able to work out how many moles of HBr were initially present. So I'm going to do that. Number of moles is concentration times volume. The concentration they told me initially was 0.45 moles per decimeter cube. And the volume initially was 90 cubic centimeters. Remember, I've got to change that to cubic decimeters. So that's going to be 0.09. And if I work that out, I get 0.0405 moles. Okay. That's how many moles were initially present. So that's the total number of moles. If I use Mr. Reggio's equation then, total number of moles is 0.0405 is equal to, I don't know what this is, the reacted moles. So I don't know how many moles of my HBr actually reacted with the zinc hydroxide. But I know that at the end of that reaction, I was left with 8.25 times 10 to the negative 3 moles. Okay, if I go back to this thing over here, I had worked out that the number of sodium hydroxide, the number of moles of sodium hydroxide needed to neutralize my excess Br was 8.25 times 10 to the negative 3. And because they react in the ratio 1:1, I must have had 8.25 times 10 to the negative 3 moles in excess. Okay. So I know from the information, the new information that they've given me, giving me the concentration, I've got the volume, I can work out the number of moles that was initially present in my flask. And I've done that. I get 0.0405. And the total number of moles must equal my reacted moles. Okay, so that's the reaction with the zinc hydroxide, and I have no idea how many that was, but I know that once that reaction had finished, I was left with 8.25 times 10 to the negative 3 moles of HBr. Okay, and so this allows me to work out how many moles of HBr reacted with the zinc hydroxide, and if you do that on calculation over there, you end up with 0.03225 moles. Okay. Right. So now I want to go back to this thing. Okay. It all boils down to a mole ratio. All of these things are ratio problems. So I know that when I react my zinc hydroxide with my hydrogen bromide, they react in the ratio 1:2. Okay. But I've just figured out that the number of moles that must have reacted with my zinc hydroxide is this thing over here. Okay. So my mole ratio is 1:2, but I've just figured out that the number of moles that reacted with my zinc hydroxide, number of moles of HBr that reacted with my zinc hydroxide is 0.03225. Okay. And because they react in the ratio 1:2, and I keep that same ratio, then I would have to halve it to figure out how many moles of zinc hydroxide I had. So I'm going to halve this thing over here, and I'm going to get 0.0161. Okay, that's still in the ratio 1:2. So I know that 2 moles of hydrogen bromide would react with 1 mole of zinc hydroxide. So if I have 0.03225 moles of hydrogen bromide, then I must have used half the number of moles of zinc hydroxide to react with it. Okay, so now I know how many moles of zinc hydroxide reacted with my hydrogen bromide. Okay, and then you go back to your old equation, moles is equal to mass over molar mass. And you want to know what the mass is, so mass is number of moles times my molar mass. I know how many moles of zinc hydroxide I used. I used 0.0161. I can figure out the molar mass of my zinc hydroxide. I just need a periodic table. I think zinc is 63.5. I don't have one with me, so just double check. Plus, I need to add to that 2 of my OHs. Oxygen has a molar mass of 16. Hydrogen has a molar mass of 1. So that's 2 times 17. And when I put that into my calculator, 0.0161 times 63.5 plus 34, I am going to get a mass of 1.57. Let me just double check that. 0.0161 times 3, 4, 5 plus 34. Yeah, 1,56975, which you can round off to 1,57 grams. Any questions? Do I need to go through that again?
No, I'm going to chat to them for the last 14 minutes before they go to bed.
Okay.
Right, so, hope you've learned something so far. But just to round up, what I want to show you is that with stoichiometry and with these excess calculations and etc., it all roads leads to moles. Okay? Now, when you do calculations, you always go back to the equation, and the equation tells us what ratio the moles are. Okay? And sometimes we have to calculate those moles okay, so let me just explain 7.3.2 again. So at 7.3.2, we wanted to calculate the amount of the mass of the zinc hydroxide. And that was, and I remind you, let me just run through this again. So you've got zinc hydroxide plus HBr goes to zinc bromide plus water. And if you put a 2 there and a 2 there, it's balanced. Right. The important thing is that it is always an excess calculation. It is always an excess calculation.
Could be, yeah.
Right. So with an excess calculation, we look at the excess moles. And the excess moles is always equal to the reacted moles plus, the total moles, my mistake, is equal to the reacted moles plus the excess moles.
Yeah, thanks. Sorry, I don't have a periodic table with me. You're quite right. The molar mass of zinc is 65. Thank you.
Right. So, the total moles is the reacted moles plus the excess moles. So we've calculated the excess moles in the previous calculation to be 8,25 times 10 to the minus 3, which is 0,00825. We give them the total moles of 0,45. Is it 0, 0? No, that's the concentration. So if I want to calculate the total moles, I must go moles is concentration times volume, which is 0,45 times 0,09. And that gives us 0,0405 moles. Right, so remember, with these excess calculations, it always comes back to this little equation over here. I've got the total moles, I've got the excess moles. So the reacted moles is obviously the total moles minus the excess moles. So the moles reacted is equal to 0,0405 minus 0,00825, which gives us 0,03225 moles. Right, so back to the equation, total moles, excess moles, reacted moles. So in the reaction, and I go back to the top of the page, there's the reaction. The mole ratio is 1:2. So the moles of zinc hydroxide is equal to 0,03225 times a half, because the ratio is 1:2, and we get 0,0161 moles. Right, so now I have the moles of zinc hydroxide that reacted, and quite simply, in the middle of the page, I will show you that mass is equal to moles times molar mass. And now that we know that the mass of zinc is 65, the number of moles is 0,0161 multiplied by, and I add them all up,
65 plus 34, 99.
65 plus 34 is equal to 99, and the mass is 1,59 grams. Okay, right. So somebody asked me to go over that again. I went over it again. But what I actually want to tell you in the last few minutes is about, as you can see, everything over here is about moles, moles, moles. So let me tell you about moles. So we all know that the mole is a number. And that number is 6,02 times 10 to the 23. So the mole is that number. And that 1 mole is that amount of elementary particles as can be found in 12 grams of the carbon 12 isotope. So because it's a big number, we don't want to run around with big numbers all the time. So we've named that number as a mole. So if I'm working with a solid, I can turn grams to moles using moles is equal to mass divided by molar mass. So that's for a solid. So with the zinc hydroxide, it was a solid. So moles is equal to mass over molar mass. If I have a liquid, in our case solution, a solution is an aqueous solution where something is dissolved in water. I've got moles is equal to concentration times volume. So in our cases, we move between, we work with solids and solutions, and we use these equations all the time, and these equation leads us to the moles. And of course, the other state of matter is a gas, and this only happens at STP. We have moles is equal to volume over molar volume. So if we were given, they say at STP the following volume of gas was formed, we can find out the moles of that gas that was formed at STP. So it's a good idea for you to write down this diagram, and it will guide you throughout. So what have we learned?
Are you going to give them the molar volume so that remind them of it?
Okay, so at STP the molar volume is 22,4 decimeters cubed. Right, so what have we learned for the day so far? We've learned a couple of things. We've learned, and the skills is more important than the answers. We've learned that when we work with excess calculations, we've got to look at acid plus base, and we end up with a mix. So we need to make these little drawings to help us through. We need to make these little drawings to help us through. We also learned that if there were both solutions, then V1 and V2, and then the mix has volume V1 plus V2. Sometimes, when there's excess, the mix has excess, we sometimes react it with another base or acid, depending which one is in excess, and we can neutralize the mix. And that is called the back titration, where we neutralize the excess acid or base, and we can then calculate how much was left over. So this part is called the back titration. And back titrations are particularly useful for volatile substances, substances that evaporate quickly like ammonia. Because if I took ammonia and I took a titration is a very, very slow process. And if I dropwise add acid to ammonia, by the time I've neutralized, half the ammonia has evaporated, and I never know, I won't get to an accurate answer. So what we do, we just dump excess acid into the ammonia, let all the ammonia react immediately, and then we can find out how much excess acid there was by reacting it with sodium hydroxide, and then we can go work our way back to ammonia, for example. And the other very, very important thing that we've learned today is that moles in excess plus moles reacted is equal to the moles in total. Okay, so you need to take this. I'm going to leave this on during the break. So for those of you that want to take down this little piece of wisdom over here, and then we'll start again at 11. You have a 15-minute break. I will leave that on for you, for those of you that want to take that down. In the second session, we didn't get to the third question, but we got through, I think, enough for you to be able to tackle the third question on your own, and your teacher can help you once you've solved it, once you get back to school eventually. Right, so I will see you at 11, and we'll start with rates of reactions. Enjoy your 15-minute break. There we go. Right, good morning. We're back. Okay, so what we're going to do is we're going to look at November 2019, which is the full paper, and we're going to go to question 5, which is the question that relates to the rates of chemical reactions. Okay, we're going to do that. For some reason or other, the question on rates of reactions is quite often not answered well in the exams. And that is because quite often there's a little bit of thinking that you have to do, and you have to respond to questions. And sometimes it's a concept of language and so on, and sometimes it's not. Okay, so let's just have a look at this question over here. So the calcium carbonate in antacid tablets reacts with dilute hydrochloric acid according to the following equation. Now, when I look at this, it reminds me that this is the reaction of an acid plus a carbonate. And there are 4 reactions that we need to know. And it comes up from grade 9, acids and bases. An acid plus a metal is a salt plus water. An acid plus a metal oxide, an acid plus a metal is a salt plus hydrogen. An acid plus a metal oxide is a salt plus water. An acid plus a metal hydroxide is a salt plus water. And an acid plus a metal carbonate is a salt plus carbon dioxide. Now, 2 of those reactions end up in gas formation. The one is an acid plus a metal. The acid plus a metal gives us hydrogen gas. The acid plus a metal carbonate gives us carbon dioxide gas. And those 2 reactions are very, very, very important for rates of reactions, because quite often we measure the amount of gas formed, in this case carbon dioxide. I don't know if this relates to that, but let's see. So, in the above reaction, is the above reaction exothermic or endothermic? Give a reason for your answer. If I look at the equation, we clearly see that delta H is negative, and we know that when delta H is negative, the reaction is exothermic. Notice, the one other thing that I just need to mention about question 5 and rates of reactions is that single arrow over there. That single arrow is very, very important, because you've now learned about reversible reactions and double arrows and etc. And all of a sudden, because you've learned about reversible reactions and double arrows, everything is reversible. With rates of reactions, we're only looking at one-way reactions. So this is a single reaction going from left to right. It's not reversible. So in this case, when calcium carbonate and hydrochloric acid react, it forms calcium chloride, carbon dioxide and water, and delta H is negative. In other words, energy is given off during the reaction, which means it's an exothermic reaction. So if the question is it exothermic? Yeah. Or endothermic? It's exothermic. And why? And the reason is because delta H is negative, energy is given off during the reaction. Right. An antacid tablet of mass 2 grams is placed in hydrochloric acid. After 30 seconds, the mass of the tablet was found to be 0.25 grams. Calculate the average rate in grams per second of the above reaction. Okay, let me just go to the document reader. And we're back at the document reader. Right. Now, to measure the rate of a reaction, we can either measure the rate at which reactants are used, or we could measure the rate at which products are formed. Okay, so to measure the rate, we can either measure the rate at which reactants are used, or we could measure the rate at which products are formed. So in this case, our rate of reaction is, and we look at the start, I had 2 grams of antacid, and the antacid is in the calcium carbonate in antacid tablets. So we are measuring the change in the reactants over the change in time, and our change in the reactants in this case is 1,75 grams divided by 30 seconds has elapsed, and the average rate is equal to,
I think it's 0.6.
on the calculator, 1.75 grams divided by 30 is equal to 0.06 grams per second. Right. Next question. The antacid tablet contains, I'll just show you the question again. The antacid tablet contains 40% calcium carbonate. Another antacid tablet of 2 grams is allowed the antacid tablet contains, where am I now? The antacid tablet contains 40% calcium carbonate. Another antacid tablet of 2 grams is allowed to react completely with HCl. Calculate the volume of carbon dioxide that will be collected at STP. And again, when we look at it now, I remind you of what we did earlier on. Right, so there's a question, and the question asks, where do I get the 1.75? And the 1.75, simply is the 2 grams. Right, I started with 2 grams, I ended up with 0.25 grams, and I get 1.75 grams, which is the change. Right, so I remind you again of what I said earlier on. And what I said earlier on is everything is with moles. Okay? And then we said that if we have a solid, moles is equal to mass divided by molar mass. And if we have a gas, moles is equal to volume over molar volume. And the reason why I'm drawing this again, the molar volume being 22,4 decimeters cubed, is simply because, again, we have a situation we have a situation where calculate the volume of carbon dioxide at STP. So as you can see, I told you before, everything relates to moles. 40% of the calcium carbonate, of the tablet is calcium carbonate. Forty percent of the antacid tablet contains calcium carbonate, which means if I look, right, so the calcium carbonate is 40% of the tablet. Right? The tablet is 2 grams. Of which 40% is calcium carbonate. Right? So the mass of calcium carbonate is equal to 0,4 times 2, which is 0,8 grams. Which means the moles of calcium carbonate is equal to mass divided by molar mass, which gives us 0,8 divided by the molar mass of calcium carbonate. Calcium is 40, carbon is 12, oxygen is 16. So if I add the 40 plus 12 plus 16, that's 100 grams. Right? Which gives us 0,008